is Priya Pahwa, and I recently completed my second master's, which is MTech in Quantum Computing. And currently, I am working on in the interface of both academia as well as industry. So I'll be talking about quantum algorithms in action. So yeah, so let's move on. So we will be actually talking about hands-on discrete implementation of certain algorithms. And before I start, I really want you all to be very much free because I have tried my level best to make it for student friendly so that you get each and everything what I have, whatever I have put. And also, like I will be having my eye on the questions, so I'll try to answer each one of them as possible as I can. And also, don't worry about the material. I'll be sharing it on Discord, all the Jupyter notebook files, which I'll be showing you and explaining you. So don't worry about okay. So also before well versed with some terms which I will be using because I know today I'm going to bombard you with so many jargons and circuits and all of this stuff. So yeah, let's just begin what is in there. So let's begin the action then. Okay, so first of all, I'll be talking about quantum gates. For those who have heard previous sessions, well, fair enough. And for those who haven't, it's very easy. You can just take a grasp. Okay. So yeah. So what are quantum gates? So there are like I will be explaining some two, three gates which I will be using in certain algorithms, and I will be explaining step by step everything like what is happening, how can you actually simulate, and the probabilities associated, everything. So let's move on. So first is the Hadamard gate. So quantum mechanics works on the principle of superposition. That is all at once in a single layman term, if I can explain. So all states at once, the existence of all states at once. So basically what happens in this is like if we say my input is ket vector 0 and I'm applying Hadamard gate, so it converts it into like 0 plus 1 by root 2. Basically, it's a superposed state. And again, if I take it to 1, so it goes to 0 minus 1, and it's represented somewhat like this. Now, moving on, if I'll talk about X gate, that is quantum NOT gate. So here what happens is, like if I give my input as get 0, it will turn to get 1, and vice versa. If I give get 1, it will turn to get 0, right? So it's like analogy I would be giving kind of flip, like switching of a switch. I mean, on and off. Like it's a classical analog of the quantum in which I'm trying to explain. And this is how it looks like. So I've kept it like very basic so that you can get everything because in a algorithmic implementation also I'm not gonna use too many qubits in order like I don't want you to confuse. I want that each one of you should be getting whatever I'm saying. So next is C naught gate, that is control flip gate. So it's actually a two qubit gate. The previous two gates which I have talked about are actually single qubit gates, and this one is a two qubit gate. So what happens is, suppose there is like, as you can see, there are two nodes kind of thing over here. One, this is my control and this is my target, right? So what happens is, if I provide input 0, get 0 to my control, so the target won't change. But if there is 1, then it will apply an X gate to the target. Like the thing I'm trying to say is, suppose I'm applying 0, 0. So my output will also be remain 0, 0, right? If I'm giving 0, 1, it will be remaining 0, 1. But if I give 1, 0, so here comes 1, and what did I say? I will apply X gate to the target. That means that 1, 0 will become 1, 1. And further, if I apply 1, 1 gate, so again it's 1, right? It will change it to 1, 0. So this is how this C naught gate works. And it's a very, I would say all these three gates, majorly what I will be going to talk about plays a big role in that. So, okay. Yeah. So now let's talk about what are the major requirements in the quantum algorithms. So the major requirements are like quantum parallelism, one more jargon over here for you all, and quantum phase kickback. So first let's hop on to quantum parallelism, right? So, okay, so this is a analogy which I'm presenting it to you. Suppose there's a box and it's a password protected box, right? And you have to open it. What you will do classically? You will try each key, each passcode, like open. Worst case scenario, the end one will open, right? But there's a quantum trick that comes into existence. So the quantum trick says, let's say we have a function fx that checks something, right? So in classical computing, one value gives one output of fx. But in quantum computing, you input a superposition of many values of x and you get a superposition of all fx values at once. So this is how this, like, it's a game changer over here. So mathematically, I have like expressed it for all of you. So basically, these are my inputs. It's in a superposed state, as you can see. And then when I apply function, it becomes somewhat like this. Basically, x comma fx of get, x comma, again, this is fx, and so on, so forth. So all functions evaluations in just one step. It's a magic. So this is very important. Like keep in mind some of these things because this will help you in figuring out what is happening further. Okay, as it's a bit tricky thing which is going to be there. So now, but there is a main question that might be popping up in your mind right now that why don't we just see all answers, right? Why is there like this one answer coming up? If we are providing superposition, then my answer should also be coming into superposition that might be popping up into your mind. So I'll just pass one statement that in quantum mechanics, an act of measurement disturbs the system. Okay. Because when we measure a quantum state, it collapses the answer to one state. Okay. So our quantum algorithms must be carefully designed in order to get the correct answer, right? So this is how it works. Again, I'll repeat the same statement. The act of measurement disturbs the quantum system, or I should say the act of measurement just collapses the system to a one system, right? So further, the use case of these like jargons, which I already told, it's actually an algorithms only, like which I'll be talking about, Deutsch algorithm, then Bernstein-Vazirani, then Simons, then Shores, then there's Grover, and there are many numerous algorithms that are still in progress. So now let's understand what is quantum phase kickback. So there's, I present an analogy once again. Suppose you shout into a cave, right? What happens? Your voice comes back as an echo, right? So it's kind of like the cave is not getting altered, your voice is getting altered, you are getting altered. So do you, whatever you hear, it's like a phase flip, which you are hearing, right? For example, if you might have heard, like read in your 11th, 12th class, that example of momentum, throwing a ball to the ball and the ball comes back. So the momentum becomes minus 2 MV, right? So it's somewhat similar to that. I don't know if it fits into the analogy or not. So I'm trying my level best that you get it. So now I'll make you understand through what I'm actually mathematically and technically what it means. So normally a controlled U gate is there, which applies to the target when the control is one. But in certain cases, what happens is, like in certain cases, instead of changing the target qubit state, the action of U, it like kicks back. There's a phase factor that comes into picture with this. So let's move on. So mathematically, I'll try to explain. So as you can see this equation, Q psi, U catch psi is equals to lambda psi. This is an eigenvalue equation. This is my operator, which is acting on the state psi. And this is the eigenvalue of this state, right? So now what they are trying to say is, like, if we apply 0, it won't change. But if we apply 1, my like eigenvalue comes into picture and it gives me a kind of a phase on the control. It gets as imprinted phase on the control. Okay. So now why is it useful? Like, where is it used? Why is it useful? Again, like in Bernstein-Vazirani, it is used to encode hidden information like strings in Bernstein-Vazirani algorithm, in factorization problems, which is Shor's algorithm, and to implement powerful tricks like quantum Fourier transform indirectly, directly. It's used, okay? So these two were the main things which I explained. First was quantum parallelism, and second is quantum phase kickback. There are other two also, superposition and interference, which are actually used in the starting and in the ending of an algorithm. So let's move on. So now I'll be talking about another jargon, which is oracle, magical words. So actually, it's a black box. It's used in quantum algorithms to evaluate a function without knowing what is happening inside. Basically, it's kind of like if you see you whenever you go to a vending machine, you put the coin and you get the desired position. But do you ever care about what is happening inside that machine? No, right? So we don't care whatever is happening. We just care about what the result is. So and we walk away. So this is just like the oracle is just like the vending machine. Okay, we don't know the internal structure, but we are focusing on the results. But obviously, we have to learn. So we will be learning about what is oracle and how does it function. Because for every algorithm, this oracle is different. And when I talk in quantum regime, by the word oracle, I mean a combination of circuits, combination of gates. Okay. So moving on, this oracle in quantum regime, I would say like it should be as fast and as efficient as possible. And and we want that in order to reduce the complexity of our algorithm, we want as few queries to be called as possible, right? So we are basically trying to minimize the complexity. So next is yeah. So this is the algorithmic timeline which is prevalent. So firstly, it was Deutsch-Jozsa algorithm, which came in 1992, then Bernstein Vazirani, and then there is Simon, Shores, Grovers, and so on and so forth, right? So now let's hop on to Deutsch-Jozsa algorithm, which is a one-shot function detection. So what do we mean by one-shot function detection is basically it is actually used to detect whether the provided function is constant or is it balanced, right? So let's understand what do we mean by function is constant or balanced. So suppose we have a black box that is Oracle, right? And it takes n bits and as input and returns either 0 or 1. So the problem involves determining whether this function is constant. Like if my function is returning all zeros or all ones, I'll call it as my function is constant. And if it returns all half zeros and half ones, then it will be balanced, right? So classically, what you do is worst case, you might have to check it like 2 to the power n minus 1 plus 1 times. You can check it. Like I'll show you a truth table and the last, and you can maybe figure out what I'm trying to say. So yeah. So like if I would like to give an analogy, we can say, yeah, you have suppose a deck of cards and you have to find out like how many are red and how many are black. So you'll put one by one, you will take it out and then you will figure out if all are red, then it's constant. If half are red, half are black, then it's balanced. So this is what it actually detects. So let's now look at its working. So the working which I'll be talking about right now, this is actually valid for all algorithms. The generic working, I would say. First of all, what we do is we initialize our qubits, okay, and then we do like keep it in a superposition state. How do we keep it in a superposition state? By using Hadamard gates, which was the first gate I initially discussed, okay. So basically turns 0 to 0 plus 1 by root 2 and 1 to 0 minus 1 by root 2. That's the superposed state. Then, then we pass it to the Oracle query. Now, Oracle query will be amended as per our algorithm, like whatever algorithm we will be talking about. Okay. Then there is the interference which will be happening after the oracle. Basically, I will be passing it through again Hadamard gates. And then measurement, which is the classical measurement. That's what I said. An act of measurement disturbs the system because we want our answer not to be probabilistic, but to be a precise particular answer. That's why we do the measurement. Okay. So now let me show you again a circuit. So here it is. So now, as you can see, what we have done is there's this four qubits as of now. Okay, I will say four, but I'll clarify why I'm coming up to three. So basically it's Q0, Q1, Q2, Q3. And here we have initialized it to 0. For simplicity, for every algorithm, we initialize it to 0. And then we provide it to HADMUD in order to minimize our queries. So basically, what happens is initialization 0, 0, 0. Second was superposition. So I put the HADMUD bit. Now then we pass it to the oracle. Then this is the interference which is happening, and then this is the measurement, right? Now what is this Q3? Now you might be thinking like why X gate, why H gate? I'll tell you. So this is actually used for a jargon which I used previously, that was quantum phase kickback operation. Basically, it takes or it helps in basically getting me the output. It allows not my input function input should not be overlapping with my fx, and it brings a phase change, basically -1 to the power fx change here. So that's why we use it over here. So we my all of my qubits are initialized to 0. I'll put x, it changes to 1. Then I put HADMUD, it changes to 0 minus 1 by root 2. Like I'll tell you, I have not included all the mathematics because I don't want you people to get bored. That's why I'm just explaining what is happening in the circuits. Okay. So then we are not measuring it because it is just a helper qubit, right? And in technical terms, in quantum terms, I should say, you will find out in textbook, there's a word you use, ancilla. That is the ancilla qubit. And this is the classical measurement that is being done over here, okay? So, so this is you can say a generic circuit, and actually this, now we will be focusing on what is actually the oracle. Now I will move on to the Qiskit implementation of Deutsch-Jozsa algorithm. Is my screen visible, right? Yeah. Okay. So here we go. So this is the implementation of Deutsch algorithm. We will start with 1 qubit. Okay. So what we did, we have imported all the libraries required from this kit, and then we have this uh, actually described our quantum circuit, and we have put Hadamard, X gate Hadamard, and this is the quantum barrier just to differentiate like which part is what. So this is the initialization part, this is the superposition part, and then we have gave a condition like if balance condition is true, then we'll apply a C0 gate. Okay, so this is where this phase kickback operation comes into picture. Like from here, it is passing to here, -1 to the power fx is coming into picture over here. Like when you will do the mathematics analytically by hand, that match, then you will get what it is happening over here. If you want, I can share the material with you on the spot. That's not a problem. But I have not included that over here. And then we have described our like circuit. QC.draw is actually the command for visualizing the circuit. Then even I have actually visualized the Bloch representation, which is used to tell whether my qubits are in pure state or in mixed state. So as you can see, my first qubit, that is Q0, is in one state, right? And my second is in the like state where it is added a phase. That's why it's not either 0 or 1. You can see. Now here it's coming to 1. Now when I measure it, finally, like giving using the simulator and the transpile command, so you see it's this. We get all like fully probabilistic for counts for 1. So this is very simple. Like single qubit we have taken and an ancilla. Okay. Now moving on to 2 qubits. So here we go, the same process, simple sorted, H, H, X, H. So this is two qubit and this is my ancilla. Yet again, we have given the same conditions and I have applied the C naughts. So you see these barriers, this is my oracle. As I initially said, oracle sounds like a magical word. It's black box, but for us, it's not a black box. We are describing it. We are giving it the conditions because that's what we want from our algorithm in the end, right? And that's how we get. So now I'll be sharing this file with you, and I want you people to just give a command for the histogram to be visualized, and then you interpret what is happening. And if you find anything difficulty, anything, that you can just let me know anytime, anywhere. Okay. So here we go again with my slides. Yeah. So just for the sake of explanation, I have also made one truth table for you people. Yeah. So this is just an example to Tribble. Don't look behind the logic. Like I'll be explaining what kind of function it's there, right? So so the first circuit which I shown, that was fx equals to x. Basically, this is hidden. So if that would be the case, then my function would be 0, 0, and 1, 1. So you can clearly say it's balanced. Okay. But this Deutsch-Jozsa algorithm, it's actually for n systems, n qubit systems. Now here I'm taking two qubits, right? So let's suppose my function is giving me the result is x2. So now you can say like my function is what? It's balanced, right? Two zeros and two ones. And the one which I showed over there in the last, where two C naughts I put, that was x1 XOR x2. So that's how it differs. It differs with the conditions. Oracle differs, Oracle varies with whatever function we are looking upon. Okay. It has got great deal of importance. Like we have got exponential speed up because of this algorithm. And one more thing happened, like it was the first algorithm to be coming up in 1992. So it's like set up a great foundational milestone for people to work upon, because it has laid that generic idea, like what is needs to be done, where the amendments needs to be done, right? So this is how it has set up a milestone for all other algorithms to come into play. So now, next over, we have Simon's algorithm, which is popularly known as the search algorithm. Sorry, not search. Basically, it's a period finding algorithm. Sorry. Yeah. What do we mean by period? First of all, let's just look at the complexities involved, and then I'll be breaking it down into simpler steps as to what is happening here. So let's suppose we are given a black box, okay? And this is a function which goes from n bit strings of 0 and 1 to again this. And there is a promise comes with along with it that there's a secret string s hidden in it, okay, of n bit strings. Now, the point is that the function satisfies this condition, okay? And the oracle which we are talking about, obviously, it's a unitary operator. And it has hidden that secret string S inside its mapping like this. Basically, we know oracle is a unitary operator, I already told, and we have applied qubit, initial qubit x, to 0, and then it goes to fx. Now, what is happening is it should satisfy this condition where this arrow is marked. Now, sounds very I would say very weird and haywire, right? Now I'll simplify this for you because this is very important to to people to know. That's why I have put it over here. I'll explain it using a truth table. Basically, this secret string is actually the period. In layman terms, I would say how many times my function is repeating. So let me explain this with the instance of truth table. So you see, this is an example truth table. For instance, as you see, this is the input. All like sorry, these are all qubits. I should just tell you. So and then this is 0, 1, 1. This is 0, 1, 0, 0, 1. So can you see like how after how many like time or how many periods it's increasing? 0, 1, 1 is increasing after 3. 0, 1, 0, it's again increasing after 3. 0, 0, 1, it's again increasing after 3. So by looking just as this, we can see that, yeah, the period for this is 3. So that means it's going like 1, 1. So now, again, I'll take you to the Qiskit implementation of this algorithm. Yeah, so here we are. Yeah, yeah. So see, we are working for s is equals to 1, 1. Okay. So as of now, I know the string. That's why I've designed the oracle. So because I am kind of giving you a demo, that's why I have designed my oracle in such a way so as to extract that hidden string, right? So again, I imported all the libraries, and this I have like hard coded for the Simon oracle. Basically, I have described sorry, I have described my quantum circuit and the number of qubits. So this is the Simon oracle, which we have described. Okay. And now we are building the circuit. Now here I am talking about a 2 qubit circuit. Okay. So in the Simon's algorithm, actually we use a concept of like 2n and 2n qubits. Okay. So what happens is I have provided the Hadamard's in both the qubit, okay? And then we have called the oracle, then again the Hadamard. And when we call the oracle, as you can see, we have already given the conditions for our oracle, which is this. Now you might be thinking like, okay, if it's 2n, then what is the use of this q3? Because the function is demanding that, right? Like it says we have to use 2n qubits at the end. That's why it's there. So it's of no problem. It's not of use. But when you go to n number of qubits, you will find out that it's becoming useful, right? So that's why I kept it very simple for you people so that you can get it. Now, again, we have simulated the circuit and these are the results. Now, this is valid for 0, 0, and 1, 1. Now, I'll tell you what are these. I know this might be like very much confusing, like why is this coming up? So let me explain that. Yeah. Okay. So let's just break it step by step what is happening. Okay. So first of all, what we did, we initialized the qubit, initialization, right? First step. So we initialize the qubit 0, 0, right? So when we initialize the qubit, other states are not coming into picture, right? So that. Next, what happens is, like we after first had merge on input, all my states are in equal superposition, like uniform. Okay, so what happens is all the amplitude becomes 0.5, 0.5, 0.5, 0.5, as you can see, and so forth, the probabilities, right? Next, what happens after oracle? Now, this is the major thing which you need to get. So like, okay, wait, yeah. So after oracle, what happens is oracle ensures that the function should follow x or s. So s is the period, okay, and this maps to the same output. So basically, what happens at the end when you will solve it mathematically, you will see that these pairs are getting entangled with the same ancilla. Okay. And after that, the effect on the input is that amplitudes remain, but now these pairs become correlated. Okay. So that's why we were seeing the two outputs. I'll tell you again that. So basically what happens is 0, 0, and 1, 1 share the output, 0, 1, and 1, 0 share the output, right? So then state becomes a superposition of correlated pairs. That's how it is working, further making it more easier for us. So now we apply Hadamard's again on the input register. If you want, I should go back to the circuit. You can see from here. Yeah, this is again the Hadamard's which I'm talking about, and this is the C naught gates, right? So yeah, so this enforces the condition that y dot s is equals to 0. Okay, now s is my period and y is my y0 XOR y1. So what happens is I want that this should satisfy y0 XOR y1 should be equal to 0. And my 0, 0, and 1, 1, those two combinations that were coming out now in histograms, that were actually satisfying this. And when you see, it was orthogonal to S also. So that's why it goes on handy with all the conditions. That's why we are trying to figure out the basically the values of y0 and y1. Yes, it helps in finding out the hidden, but here, since I all 0, 0, and y1. So hence now what the amplitude becomes? For 0, 0, it becomes this, and for 1, 1, it becomes this, and thus the probabilities. So you see, this becomes 0 at the end. So by repeating the experiment enough times, we can actually collect equations to solve for the hidden string 1. So now last step becomes the measurement. And measurement actually collapses the input register to the valid Bayesian chance of getting 1, 1, which satisfies and goes well in accordance with my hidden string, or I should say period S. Okay, that is y dot S is equals to 0. This is the main condition that we should remember in this. So this is all about Simons. But next is the question, why are there two outputs in the Qiskit implementation part? So Simon's algorithm actually doesn't directly give you S, okay? It each run gives a random Y such that it qualifies for this expression. Already mentioned, right? Classical algorithm. Okay, so for classically, you have been like exponential, like 2 to the power n by 2 time. taken. Like this much of queries will be required, but quantum actually reduces down to polynomial. That's a bit exponential speed up if you say it that way. So yeah, so this is all about diamonds. Now next comes up rovers, finding a needle in the haystack. You can see this picture. Suppose like you saying it only took you like these many seconds to find out the needle in the haystack. So yeah, moving on. Suppose you have got a treasure box and there's another box which have like millions of keys and you have to open that treasure box. What you will do? You will just take the keys one by one, try to open it. Lucky enough, you will get it in 100, 200 key. Worst case scenario, the last key would be the one which is to be opened. But quantum gives me an upper hand. That is, Grover's algorithm can help me finding the right key in about just 1,000 tries if there's a million of keys present. Okay. So this was the like classical analogy which I gave you right now. So let's move on. So let's focus on what actual problem it's also. It's actually the search algorithm, very famously called as. So it searches for a marked item in an unsorted list of n items. Okay. So basically, when you are given a function, so if that x is the solution of that function, the my system will collapse like the it will be getting as one in the end, otherwise zero because it's not the solution. So basically, what we have to do, we have to find the value of x. We have to find that marked state where my fx is giving me one. Basically, the state which I am aiming to find out in that whole number of sets of unstructured list. Okay. So let's see how it works conceptually. First, let's understand the concept behind it. First of all, yet again, we are preparing the superposition. We are using Hadamard gates to put all n possible states into equal probability. And this is how we write mathematically the Hadamard operation. Now, this Grover algorithm, I would just like to add up, like it has an oracle plus it has a diffusion operator along with it. So what it does is, oracle is a marking step. Okay, what it does it will among all that list, it will flip the sign of the mark state. Okay, okay, and like it will flip the sign of the amplitude of that solution, basically the marked item, as I mentioned. And then this diffusion, the amplification step. This is the reflection about that amplified state, and it's increased the probability about that average by inverting it, right? So we have to repeat it like iterations. We have to repeat it like root n steps until and unless all the items in that list goes like to come down, and that amplif probability that marked item which we are looking goes up to highest probability. Okay, so that's how we find out that this is the one which I was searching for. Okay, so this is actually Rover's algorithm. It has got quadratic speed up, I would say, as compared to the classical analog, and it is very, very useful in uh, various research and studies. I think still there's somewhere some amendments are going on this algorithm. So yeah, so this is what actually happens if I would say in a nutshell. This is the initialization. We create superposition of all items using Hadamard gates. Then using Oracle, we use the phase flip operation. Then amplification is done by marking amplitude, like boosting the marked items amplitude. That is the diffusion operator. So this is the step-by-step probability evolution. I would like to show it to you so that you can get better actually what is happening, because all of these jargons, diffusion operator, oracle, what is happening, you might not be getting. But you see, through probabilities evolution, we would say time and again, we get to understand better what is happening. Okay. So first is initial state. Initial state is always 0, 0 for simplicity. So obviously the probabilities is for 0, 0 is 100%, right? Next is after Hadamard's. Again, uniform I've seen in Simon's as well. And probability will become 1 by 4. So hence the table it's there. Now, after Oracle flips the amplitude of the mark state, 1, 1. Okay, so 1, 1 amplitude becomes minus 0.5. But there is no change in probability. Why? Because it's the square of the amplitude. Anyways, negative sign is like went off, right? So the probabilities again remains the same, right? So next is diffusion operator, the major thing. So diffusion actually reflects all amplitude about their average. So average amplitude before, like before the oracle, it was this. And so average comes out to be 0.25, right? Now how do they, like how this person has actually did the evolution of this algorithm is, he found out new amplitude by averaging the twice minus the old amplitude. That is, if you see 0, 0, it was twice 0.25 and its actual was 0.5. Amplitude. So it becomes 0. Again, 0, 1 becomes 0 because if you will see, it's the same one which state. This is the magic of this algorithm. It just boosts and amplifies the state which we are looking for. See, so this is how it happens. And this is the truth table. Again, 0, 0, 0, 1, 1, 0, all have 0 amplitude, but my 1, 1 goes, shoots up and gives me 1. So this was the diffusion operator which we were talking about. And measurement is that the system collapses into the mark state, 1, 1, right? Now let's look on to the Qiskit implementation of the Grover algorithm. So basically, what I'll say is these algorithms, they have different oracles, as you can see. But here we will be dividing our algorithm actually into two parts. So yeah, here it is. Wait. Yeah, here it is. So yeah, again, we have imported every required library, and first we are defining the oracle. So what we have done is we have actually used all the Hadamard and the multi-control X gates in order to like define the phase flipping operation, basically the inverting operation which we were talking about of the mark state, right? So here we have actually used it for like 1, 1 because we are focusing on 1, 1 state. So here it goes. And then we have defined our diffusion operator. Again, we have used a combination of Hadamard and the multi-control X gate. And now I have described my Grover circuit over here. So we have 2-qubit circuit, and then the mark state which we are aiming to search for is 1, 1. Then we have described our quantum circuit. Then we have made it in superposition state. Then I have called my oracle. Then I have called my diffuser operator. Then I have visualized my circuit over here. So here it is. This is the till here. Okay, I think I forgot to add the barrier. It would be much better if I would have added barriers. No problem. So yeah, here is the initialization. Here is the superposition. And this part is my oracle. This part is my diffusion operator. And this is again the measurement. Okay, so next when we run it, we'll find out we are getting 1, 1, the mark state. So what happens is all the other states just goes like to the least probabilities, and here we are getting 1, 1. So now this was all about the Grover algorithm. I would just also give you one snippet of the IBM Quantum Composer platform, because this we have done like it is the Python library. So we have done it using Python, but you can actually access it the on the IBM Quantum platform also. So this is just the snippet of the IBM Quantum platform, and you can see like we have done the same thing and we are getting the results over here. So this is what it looks like. You can actually access, or one more way for it is like we can even call the IBM using the API token of the Qiskit IBM, and then we can like run in on the real quantum computers or like present all across the globe, right? So yeah, next what we are doing is we are moving on to the uh, like evolution of the algorithms. So up till 1981, it was all experimental. In 2016, IBM came up with the revolution. Okay, and then it like provided people its cloud access, and basically classical computers were meant to revolutionize our 20th century. Quantum computers are actually expected to revolutionize the 21st century. So yeah, people are getting high hopes from it. But yeah, as I would like to add on, like whatever algorithms which we have had a glimpse on, you would see I have not talked about noise. But in real world scenario, when you just hop on to the lab or lab setup, you will see qubits are too much noisy. There are way more challenges than this. Basically, this IBM quantum platform actually allows us to simulate and know how it's working. Because you see, we were getting 100% probability. This is the ideal case scenario. Actually, we don't get 100% probability. So that's why then came up with came up the noisy intermediate scale quantum. Basically, it's like an NISQ, we should say. And then there is this fault tolerant quantum computing, which is like a long term evolution process. So it says that there should be some kind of error correcting algorithm that should come up, some kind of auto save feature that can remove noise, or to delete feature that can remove noise. So this is what is being working upon. You might have, like in the previous session itself, there was talking about error correcting algorithms. So this is what it is. So let's just like I would like to introduce you to other frameworks apart for quantum programming apart from Qiskit. So it's Qiskit by IBM, obviously, then it's Pennyline by Xanadu, and then it's Turk by Google, there's QHash by Microsoft, and then there is this Ocean SDK by DO. These are some, but there are many, like there is this TensorFlow also. So some of the frameworks are there for quantum programming. You can have access. Then there is this one with Amazon AWS, which is Bracket. So you can go into that and have a look, have a glimpse of what is happening. So now, like this is NISQ algorithms. I will like to have a glimpse, like to show you what is inside. So basically, it involves like variational quantum algorithms, and then there is this quantum machine learning. Then there is quantum simulation, and in variational quantum algorithms, there's this variational quantum eigensolver and quantum approximate optimization algorithm. So last 15 minutes, I'll be talking about this variational quantum eigensolver, a brief glimpse as to what it is. So first of all, why noisy intermediate scalable quantum computing? Because it's feasible on today's quantum computers, right? And it has got various insight into future advantages. Like you can come up with various algorithms and all the computational techniques that have been involved. You can like it actually helps us to hop into any sector you choose upon, be it healthcare, be it finance, be it AI, be it generating models, anything you can think. Okay. And then there's a hands-on learning. We can simulate, we can run, and we can get a good hands-on on this. For example, quantum machine learning is quite prevalent these days, and they are coming up with various quantum kernels and other models. So this is the kind of exposure it provides. Next is I'll talk about variational quantum algorithms. So I'll just talk like step by step, very briefly, what happens inside it. So first of all, in variational quantum algorithms, what we do is we choose a problem, okay, and we kind of encode that problem in terms of qubits. So for example, very basic and very common example is like working upon the molecular structure of hydrogen. We kind of encode that problem on qubits. Basically, we find out the Hamiltonian, uh, okay, like we aim to find out the ground state energy of the hydrogen molecule. Then we build a parametrized circuit. So by parametrized circuit, what we mean is like the circuit which has got less circuit depth, good optimized like parameters in every sense. Then, okay, just a minute. Yeah. Then there is this, we have to just basically, obviously, we will run the circuit, and then we have classical optimization techniques in order to, that's a kind of candidate that we see coming up to in order to compare with the quantum and classical regimes. And then we keep on iterating. So basically, when we run the circuit, we classically optimizes and we keep on iterating until and unless it converges down to the minimalistic ground state energy which we are aiming for. So this is what variational quantum algorithm is. Basically, this is the quantum eigensolver. So I would just add like this parametric circuit which I am talking about. In my further slides, I'll be using the word ansatz. Basically, it's like a trial wave function. For those who have actually learned about learned the advanced quantum mechanics, they might have had heard about the word variational approach. So I found it very much into that thing. So this is how it ends. Also, when we talk about variational quantum eigensolver, it's not just we are defining the Hamiltonian, right? So when I say Hamiltonian doesn't just restrict me to potential energy and kinetic energy. There are so many things associated, like the interaction energy. For example, if I am talking about some spin chain reactions, if I am talking about the evolution of that, so we'll talk about the neighboring interaction energy, its own interaction energy with the surroundings, everything. So we take it to account everything possible, and that's how Hamiltonian we'll describe. So basically, I've just given the example of hydrogen in the form of how quantum computer can handle. Then we'll move on to ansatz circuit. It's a simple parameterized circuit designed to search for the lowest energy state, basically the ground state. And then we move on to the optimizer, which adjusts the quantum circuit parameters in order to minimize the energy as low as possible, right? And then obviously you'll run it onto a simulator and no quantum hardware required in this. It's just a simulation which we are talking about right now. So now how this fits into NISQ, noisy intermediate scalable quantum. Basically, this answer is shallow. And what happens in this is like it's suitable for noisy devices because it has less circuit depth. Okay, and then there's this hybrid approach which prepares its candidate state for classical optimization to find the best parameters to work upon. And there is this tolerance to noise. The algorithm can converge even with the imperfect quantum operations, which is a hallmark of NISQ algorithms. So, like still now, error correcting is in progress. I won't say it has overcome this problem, but yeah, they people are trying, so it's just in progress. Now what can be changed, like how these problems can be changed, how can you access the problems, what can be the approach? You can change the Hamiltonian, you can change the molecules, you can change the physical system in which you are working, which requires more qubits, more terms, and other energies required, as I mentioned already. Then we can run these and see how they converge at the end. And we can run on real hardware. We can connect it to IBM computer, quantum computer, and the cloud service, which requires API token and some code changes, as I already mentioned previously. So now this is what the scope of quantum algorithms is right now. Like, see, it's an interdisciplinary field, and people are right now jumping from what they were. They are kind of like quite fascinated with the hype this has created, and it is worth the hype, trust me. So it's like hopping on every person. It's an interdisciplinary field, so it requires an interdisciplinary skill set as well, from physicists to engineers to computer science people to chemistry people. Then there is right now I heard some quantum biology is coming into picture. So no field is untouched. You see, right now this drug discovery is very much into progress these days. So they are coming up with different algorithms to solve to uh, amend this problem. And then there's this optimization problems, then AI generated models, then fundamental science, which new physics is being unlocked through quantum simulation. So this is what the quantum algorithms actually brings up for the table for people for different backgrounds. You just don't have to be. I've seen people worrying about like how do we get into quantum? What do we have to do? So see, it actually requires interdisciplinary skill set, right? So you can just start learning. And finally, I will just like end my talk workshop by saying that future belongs to those who embrace the power of quantum computing and unleash it to work. And questions here, I can just put up a few. I love to answer those, please. You could
Yeah,
just have a look, maybe.
thank thank you so much for that incredible speech. We really appreciate your time and insights. I learned so much, and I'm
Thank you.
sure everyone else watching learned so much too.
Thank
Yeah,
you, Rana.
yeah, we'll now move into the Q&A. I believe we have a few questions so far. So, how is entanglement used in speed up?
Okay, so basically, like in Simon's algorithm I talked about, when the pairs become correlated, it helps me finding out the period of the function. So that's how, for instance, I can say it is helping in the speeding up the algorithms, complexity, minimizing the complexity. And right now, also, these I would say, many people are just working on this entanglement based algorithms. So yeah, I'll I'll just share the files. I have some, yeah, on the Discord channel if people might need.
Yeah, thank you. We have a few more questions. Um, where are ancilla
Sure,
qubits
please.
used in algorithms?
Okay, yeah. So, like ancilla qubits are actually used for the phase feedback operation. It is used to it is actually preventing my input state to get overlap from the fx function. So, if you the person who has asked, I would just request you, you go into the mathematics as I already mentioned, you will find out that it's adding -1 to the power fx operation. So that's how when you get it to the end, when the oracle you have implemented, you'll get it to the end, you'll find out that minus sign is coming, which is the quantum phase kickback operation. So that's how Ancilla, and Ancilla is it's not measured. It's just a helper qubit, I would say, in order to measure what is being, what has to be, like what is the input qubits to be measured. Yeah.
Yeah, thank you. That's all from me. Amrita, do you have anything to add?
Hi, I'd love to know,
Hi, Amrita.
have you ever had to redesign an algorithm to work around real hardware limitations like decoherence or gate fidelity?
Sorry, can you please repeat? I think there's some which I couldn't hear you.
No worries. Have you ever had to redesign an algorithm to work around real hardware limitations like decoherence or gate fidelity?
Yeah, okay. I would just add on doing a simulation on the back ends and then moving on to lab and seeing the hardware. Those are really two different things. Like you will be quite mind boggled when you move into the lab and you will see what other challenges are there. Because as you mentioned, these are very important and very challengeable things which are coming up, and still people are trying to figure out what can be done. So on simulations, as I already said, for example, these basic algorithms which I talked about, you see, we were getting probabilities 100%, and it's just a way of saying, ki, yeah, I'll flip and the sign will be flipped, and then I'll amplify it, all will go down, my mark state will come up. It's just a thing of saying. But when you go into hardware thing, it's not thing. It's very difficult. Trust me. First of all, scaling is it's a very challenging. The foremost and the prominent challenge right now is scaling the qubit. So I mean, the gate fidelities and decoherence, they are the prominent challenges, add-on challenges. So yeah, it's difficult. I mean, it's totally different from whatever has been on the simulating part.
Okay, okay, thank you.
Yeah, if anyone else who's watching or anyone else has any more questions about this session, I encourage you to go to Discord and engage with the post-session channels. And we do have another session on the quantum hackathon in a few minutes, so I think we can end it here. Thank you once again for
Thank
joining
you.
us today.
Thank you so much, Rana. I would really like to thank Girls in Quantum for inviting me. And as an advisor, I really feel honored to be here with you all. Thank you so much.
Thank you for coming so much. Yeah.
Thank
Bye.
Yes,
you.
thank you
Okay.
for coming.
Bye bye.
Bye.
Bye.